Hello, fellow engineering students. It's FE question time. The voice you are hearing is William Payson. I am the Group E leader, and let's get started. I know how excited you are about all this.
Joy.
The equivalent resistance between terminals A and B is most nearly A, 6.1 kiloohms, B, 7.76 kiloohms, C, 7.16 kiloohms, and D, 6 kiloohms. You're going to find quite a few of these types of questions on the FE exam where they ask you what is most nearly the correct answer. So some of these things actually may not be exactly correct, but you're going to have to do your best. All right, everybody. So here's the original circuit. And right off the bat, the way I see this is these two guys right here are going to be the ones I need to get out of the way because these are sort of complicated. But it's really not, actually. So it just looks that way. This branch right here, you can kind of think of this as being elastic. And I can just stretch that point to that point and delete all this junk. And so two 5K ohm resistors here can be shown to be in parallel underneath this 10K ohm resistor. And we're pretty much home free at this point. We just need to do some further simplification to be able to punch this into the calculator. And these two 5K ohm resistors are going to effectively be half of that resistance, which is what you see here. And for me, I'm just going to add this guy and this guy in series. So that 2.5 plus 2 is 4.5 kiloohms, which is this guy. Now, for me, this is simplified enough to where I can punch this into my FX115 FE approved calculator. And it's just going to be series plus parallel plus series. Easy enough, right? So the final answer is A, 6.1 kiloohms. And here is Professor Okayo telling us about resistance.
Resistance is futile.
All right, moving on. So here we're going to calculate the maximum current of the RLC circuit shown down here. All right, so first off, we need to understand that this is an AC source. This is alternating current. But fortunately, all this junk right here, that's all in series. So we're giving these four choices here. So what do we do with it? We need to understand something. So this thing called resonant frequency, if you remember, is basically when current is going to be at its maximum. So we need to find the resonant frequency to solve this. And yeah, so there it is. So basically, the impedance is going to be the resistance, basically, just this guy at the resonant frequency. And basically, it just becomes this pretty much plug and chug equation after that. So you get your maximum current at your 120 volts AC divided by 10 ohms, and you get 12 amps. So answer C is correct. Here is the bonus to the follow-up question. What is the resonant frequency of this circuit? So basically, if you've taken circuits too, you probably have this already memorized. You might not. It is in the FE handbook. You can go look it up when you're taking the test. So 1 over square root of LC in this case. So L is 10 millihenries and 10 microfarads. And we basically get 3162 radians per second. Throw that in your calculator. You can convert that by doing 1 over 2 pi, and you get your hertz. And that's pretty straightforward. All right, so the magnitude gain of the transfer function that we see right here is given by this thing. All right, so when I took the FE, the second half of the exam felt like it had tons of these on it. I was a little rusty when I took it, so for me these were a little time consuming because I was trying to recall and still do it very quickly. So I would suggest you brush up on these things before you go and try to take the FE. So we'll just bang right through this one. So basically, here's the original function. And the way that you would do something like this is you can basically pull your 10 out right here and simplify this. And you can do this by hand or by calculator from here. It doesn't really matter. You're not going to be able to have a calculator that can do that. All this complex notation. You cannot do it symbolically on an FX115 FE approved calculator. So being able to do this stuff by hand is hugely important. I would suggest doing it. So here our answer is 20 dB. And because it's asking for the magnitude here, that would make this the answer. All right, folks, who's ready to do some EMAG? I know I am. I'm a dork. I kind of like EMAG. It is actually one of my favorite subjects. If you understand enough of it, there's a lot you can do with it. But anyway, so let's just dive right in. So calculate the load connected to the end of a transmission line with a 250 ohm characteristic impedance if the standing wave ratio is 2. So SWR being our voltage standing wave ratio, or as those of us nerds in the amateur radio biz call it BizWAR. That's what we do. So you can go look for the SWR equation in the FE handbook. It is definitely there. But if you're like me and you actually have this junk memorized, you can just regurgitate it. So our SWR is basically 1 plus the absolute value of gamma divided by 1 minus the absolute value of gamma. And really what that means is that if gamma is nothing, there's no reflection. There's nothing there. And if it's, half, then you get half the reflection, right? So we are given that SWR is 2 right here. And what that means is that this is that, right? So I can take, this guy, and that is that. And the way I'm going to do this is I'm going to drop these absolute value brackets just for the sake of doing algebraic manipulation. We understand what they mean. And I'm going to clear this denominator. I'm going to take all this junk and I'm going to move it up here. And the way that you do this here, just multiply it over. And then I'm going to multiply all this through. And now it is just algebra. And I can take my gammas and put them over there. And then I get this, and I can take my 1 and put it over there. And now I can solve for gamma. And I get that gamma is a third. And now I can start to do some math to calculate my load impedance. And this is also on the FE. I also have this memorized. This 250 ohm characteristic impedance is not a standard characteristic impedance of any transmission line, but they like to throw silly crap like this on the FE just to kind of, I don't know. You guys know what I'm talking about. They do all this kind of crap all the time. But I'm going to do this the way that we just did that one, basically. Since we just found that, I can plug it in. And I'm going to clear my denominator again, and away we go, right? So we can just do the rest of it algebraically. And, this is pretty straightforward. So now I can divide by 2, and I have solved for my load. And that's it. So the answer is D. 500 ohms is my load impedance. And that's the answer. Bang. More EMAG. All right, you can please just calm down. I know you're super excited about this, but this question, when I took the FE, this question almost exactly was on there. I can't really remember I think these were like 10 or something like that, but the points in space that they were. But anyway, so we're going to calculate the field intensity of the electric field at the origin due to these point charges. And if you took Physics 2 a long time ago, this might hurt your feelings because Physics 2 was not fun or easy for me. There was a lot of new information thrown at you, but you'll recognize some of these equations here in a second. But basically, our first point charge, Q1, has a 50 nanocoulomb charge located at this spot, 010. And then our other charge, Q2, is of opposite polarity, located on, it's reflected across the x-axis. I think it's something like this. I don't know. So there's a y, z's pointing at us, there's x, and what did we say? This was 010, so it would be There's that guy, and then the other one is reflected across the axis. So this guy is negative, that guy is positive. All right. So, you know what? Actually, when I took it, it might have these might have been the same charge. They might have even been the same polarity. And in that case, you do need to understand it's going to be zero if they're the same. If they have the same polarity, it's going to be the same. When this has symmetry, that's going to be the net field intensity is going to be zero. All right. So again, these equations are going to be in the book, and we're just going to use IJK notation. So that's what you see here. And and there's our r squared. There's our radius, and then we've got 4 pi epsilon naught, which that's our permittivity constant. That's what is that? That's like 8.85 10 to the negative 12 farads per meter. Something. I don't know. It's 3 in the morning and I haven't rehearsed these slides, so whatever. Let's carry on. But so basically we can just manipulate this algebraically, and we can look at this vectorially. And what I've done here is basically taken this direction and I've moved it over here. And then that allows me to group these and factor it. And, anything squared, 1 or negative 1 in this case, it's got to be 1 anyway. So then we get this simplification. And, okay. So then anyway, you can tell I haven't rehearsed any of this junk because it's like 3:30, 3:28 in the morning, and I'm tired and I want to go to bed. So carrying on. But yeah, throw it in your calculator, this whole monstrosity, or do it by hand, but that is the correct answer. Bang. All right, so straight up physics 2 question here. Calculate the magnitude of force on a 2-meter long conductor carrying 2 amps through a ½ Tesla magnetic field, and assume the angle between the conductor and the field is 30 degrees. All right, first of all, just to put some reality on this, a ½ a Tesla is huge. MRI machines max out at like 1.5 or 2 Teslas. I think some of the strongest ones in the world are a few times that, but it's a massive field. Like 1 Tesla is there's a reason we use Gauss. So like 1 Tesla is like 10,000 Gauss, something like that. So like 10 to the negative 4 Tesla or something to that effect. But anyway, so the force on a current carrying conductor in a uniform magnetic field is given by this equation, which of course is found in your FBA handbook. But it's the old force equals the current times the length cross the magnetic field, or the flux rather. That's the flux. And so basically, since all we need is the magnitude, we can do the old cross product with good old sine theta, right? So from here, it's a plug and chug. And so we can take the magnitude of this force, and we've got our current, and we've got our length of the whatever this current carrying conductor is, a wire, and we've got our huge ½ Tesla magnetic field, and our sine here, our angle, and bang, 1 Newton. Pretty straightforward. So on to the next one. So under suitable conditions, the photoelectric effect can take place in A, metals, B, nonmetals, C, liquids and gases, or D, all of the above. Now, this is one of those types of questions on the FE exam you might see. It is either something you will know or something you will not know. It really isn't something that you're going to be able to go look up in the FE handbook. It's not going to be a table or chart you can refer to. These types of questions are basically gauging how well you have paid attention in all the classes that you've long since forgot. So basically the answer here is going to be D, all of the above. And remember, if you're still struggling and you need to go back to chemistry, then that's fine. Okayo will always tell you that it's not rocket science. All right, so here's one you're definitely going to see several of on the FE. So which of the following is true about a zinc nickel corrosion cell? A, the nickel will act as an anode. B, zinc will act as the anode. C, either metal can act as the anode. Or D, corrosion will not occur. So for these types of questions, you need to understand that metals with higher standard oxidation potentials will become the anode during the corrosion process. And this is the part where you need to go looking for a chart that looks like this. All right, so this came out of this year. It's 2020 right now. So this came out of this year's FE handbook, and this will be available to you on the FE exam. And this is what that image you see is exactly how it will appear. The electrochemistry portion is actually below it on the FE. I just put it off to the right so that you can see it on one slide. And so basically we would look over here at our zinc and we would look at the potential versus normal hydrogen electrode. And we see a positive 0.763. And then we look at our nickel here and we see a 0.250. And they're both positive, so since zinc has the higher oxidation potential, zinc will act as the anode in this corrosion cell, so the correct answer is actually B. There. Okay, everybody, so in this problem, we're going to just find, the voltage out. And obviously, this is a pretty standard inverting amplifier configuration, and I can tell that because of that pin configuration. And, so just by inspection of these four choices, I know that cannot be a solution. And the reason is because it does not have the correct polarity, because my voltage coming in, right here, is a positive voltage, so therefore my V out is going to be negative, right? If you took 3401 a long time ago, this would be my advice is to brush up on this stuff, because unless you have these equations memorized just straight up, these may take a few seconds, or you can go muddle through the FE handbook and go find, this thing. And, it is in there, and you'll find this equation. And I don't particularly care to memorize this stuff. But, and the only difference here is that VA, their labeling is that this would be what they call VA. But I actually, just from solving these so much, I called this VA by habit, and this guy over here VB. I don't know why I'm drawing all over this, because I'm about to show you with prettier things. But so I'm going to derive this. I'm going to show you the way that I do it intuitively, and in this way I also never forget this stuff. So basically, I just start labeling stuff. So this is my VN, and I start identifying my currents. There's my I1 and I2, and just by habit, I call this VA, and whatever I pick VA, I just call the other one VB. So this guy is VB. And because of the way amplifiers inherently operate, these VA and VB are basically going to be the same. In real life, they are not, but for these equations and for all intents and purposes, they are. And so then I can start rewriting my currents, and like I just said, VA is about VB, right? And from KCL, we know that I1 and I2 have to be the same, otherwise, we broke something. That illegal physics, can't do that. But now I can just take my I1 and I2, I1, I2, right? And we can just start solving this straight up. And since VB is grounded, I know that it's 0 volts, and therefore, if VA and VB are the same, then I also know that VA is 0 volts. So there that is. And we can just start simplifying things down from here and getting rid of those zeros, and I can multiply R2 over the other side, and there's what that is. And now I can explicitly rewrite this in terms of V out, and there is that equation, which is the same as that. And now you can plug in some numbers. So there's my input, or I'm sorry, yeah, that is my input, and 10K over 2K is negative 5 volts, right? So again, just to clarify, this negative sign came from right here, right there. So this is my VN. And the reason that that became negative is because of that pin, and my V out is negative. So there it is. Bang. All right, and that's pretty much it, everybody. I hope you didn't forget too much of that or any of that. It will certainly all be on the FE exam, I promise. It is definitely a not an easy exam, but it is fair. It is definitely fair for a graduating senior to be able to go take and do well and hopefully pass. So that's it, guys. This is the part I suppose I should hold for some applause here. Well, yeah. Anyway, we here at Group E know that we're pretty much awesome. So we make our own awesome. Group E, You're so amazing. Yeah, we know. And that's it, guys. So I hope you enjoyed this, and I do challenge you and encourage you to make a more entertaining and informative slideshow than this. As my father always said to me, your education is what you can still remember when it's done.